So one of the things that I want to talk about today, first off, is re-emphasizing and relinking some of these functions together so that you understand how they're related. Also, I want to point out that when you're doing the indefinite integral, you know it's indefinite because there are no limits of integration, right? So it's clear. You will get a function, and the function will be a function with the same independent variable that showed up in the differential, right? So if I integrated this as f of t dt, I would not get f of x, I'd get f of t. Yes, I fell last night, so hopefully it's not broken, but we'll see. If you're wondering, I have ice on my arm. So the other thing that you need to focus on is when you do the definite integral, in contrast to the indefinite, you have the limits of integration. It's defined by definition, it's the limit of a Riemann sum, which means every box could be an arbitrary width, provided the width of all the boxes goes towards 0. That's why we write delta x sub k. Every box can be a different width. And I can do the height of the box at any arbitrary point I want. That's why we call it x sub k star, where x sub k star is just the point in that box where I chose to make the height of the rectangle. So you add up the area of all your boxes, then you take the limit as the number of boxes goes to infinity, which means the width of every box is going towards 0. That's the definition of the definite integral. And when you're done, you get a number, right? 1, finite, real number. Or, what's the other option that could happen? It's not a finite area, in which case it blows up to infinity, all right? So you either get one finite real number, which represents the area under the curve between the curve and the x-axis, as in exactly how many square feet of paint you need to paint it. All right, that's exactly what you're getting. Which means that for the definite integral, since the answer is going to be a finite number or infinity, if there's too much area, the variable that was used to produce the definite integral does not show up in the answer. It's what we call a dummy variable, right? It's gone by the end. So would I get the same result if instead of writing the integral from a to b of f of x dx, I wrote the integral from a to b of f of t dt? Would I get the same number? What do you think? You would. You get exactly the same number. The independent variable is different, but the amount of area doesn't change because the curve is in the same place. You've changed the name of the independent variable, but the curve's shape hasn't changed. So it has the same amount of area under it. So in a definite integral, the differential variable is a dummy variable, which means I can use anything I want. I mean, I could use a happy face if I wanted, or a diamond, or a star, or anything. Because by the time you're done, the variable will have disappeared entirely, and you're just left with a number, all right? So that is a fundamental difference between the two, right? Now yesterday we talked about the fundamental theorem of calculus part 1, and then we did the fundamental theorem of calculus part 2 at the end. And I want to emphasize again the connection between part 1 and part 2. So I put back up here the fundamental theorem of calculus part 1, which is the confusing one. It's the one you look at and go, I'm not real sure I get what they're doing. Okay. This basically says this is a definite integral, so we should be getting a number, except that one of my limits of integration is also a variable. When one of the limits of integration is also a variable, it produces not one finite real number, but a series of finite real numbers that are the areas between A up to that number x under the curve of f of t, right? Now, the t here is an arbitrary dummy variable because this is a definite integral. It's not going to show up in the final answer. This produces a different number, a different area for every different value of x. So if I keep moving x, the areas keep changing, all right? And that produces what's called an area function. So this is the fundamental theorem of calculus part 1. Does that make sense? Now, the next thing we did was fundamental theorem of calculus part 2. So let me put that one back up. And again, the thing that drives all of this, the one requirement that you have is continuity. And I want to talk a little bit more about that too, because your book overstates it. All right. So let f be any antiderivative function for f of x. Then the definite integral from a to b of f of x dx is equal to f of b minus f of a. Okay. So here is the connection, finally, between the indefinite integral, which produces an antiderivative function. Remember that this antiderivative function, this is the idea of I do something and then I undo it. I teach you to add, then I teach you to subtract. I teach you to multiply, then I teach you to divide. We taught you exponentials, e to the x, then we taught you the natural log of x. We taught you to take the derivative, and the indefinite integral undoes the derivative up to the constant. So this is that one-to-one inverse function to the derivative operation. That's what the indefinite integral is, the antiderivative. The definite integral is the limit of a Riemann sum, supposed to give you a number which represents the area under the curve. The connection between the two is that if you have any antiderivative function for this one coming from the indefinite integral, then the definite integral becomes the difference of the limits of integration plugged into the antiderivative function and subtracted. Specifically, if we can use any antiderivative, we can use the area, because the area is one of the antiderivative functions under the curve, right? There are millions of them, billions of them. There are infinitely many antiderivatives. The area function is just one of them. But if the area function is one of them, we can use the area function in order to find the value of the definite integral. So what you're going to do is you look at this first and you treat it sort of like you did the indefinite integral, and you find the antiderivative, right? The one you want to pick, since you can pick any one of them you want, is you want to pick the one where the constant is what number to make it easier? 0. Just pick the one where there is no constant. So we'll pick the one where the constant's 0, since I can pick any of them, and then I will plug the limits of integration into it and subtract them. And that will give me the area under the curve between A and B, all right? That's the connection between the two pieces. Any antiderivative function will work to do this. It gives us the same value. And this is coming from part A, because if A of x is equal to this, what would happen if I took the derivative of this equation right here? What did we prove yesterday using the mean value theorem? Do you remember? We ended up showing at the end that the derivative of the area is f of x. And if the derivative of the area is f of x, then the area function is one of the antiderivatives of f. There are many, but the area is one of them, right? And that's why we're able to connect the two pieces, okay? And we put them together like that. All right, let's take a brief look at the proof for that. So let me pull that up real fast. Okay, so this back on the board. One of the things that we need to do is prove this second part here so that we can connect the two. So let's take a look at the proof that's in the book. And you'll be happy to know that this is probably one of the last proofs we'll do this semester. So we don't do too many in this class. We probably do a few more in Cal 2, but this is one of the ones we do. So we start off with that the function has to be continuous. That is our requirement for all of them. Now your book does overstate that, because we did do an example where we talked about having a hole in the graph, or having a displaced point, or having a jump in the graph. And what did we decide about the area under a hole, a displaced point, or a jump? How much area is under that single point? Zero. It does have height, but there's no width to the box, right? The rectangle has 0 width. So we haven't lost any area, provided we only have how many such places between A and B? I gotta have a finite number, right? I can't have infinitely many holes between A and B. If I do, then that becomes an indeterminate form, 0 times infinity, and we can't determine using this method whether the area is finite or not, all right? Your book overstates the case. The book says it has to be continuous on AB. It does not. It has to be continuous, or it can have a finite number of discontinuities provided the region is bounded. By saying bounded, you're putting a maximum y value and a minimum y value on it. And so what kind of discontinuity are you eliminating by putting boundaries on the y values? The infinite asymptotes, right? And we said those would be a problem because you can't close the shape, right? If you poured water into the shape, it would just flow right out, all right? So just so you're aware, the book does overstate it. Hopefully this doesn't die on me. The book does overstate it a little bit. It doesn't have to be purely continuous. All right, so let me fix it. Is it back? Okay, I'm scared to move it. All right, so we start with a regular partition. Regular, again, is just convenience. Regular means all the boxes are the same width, all right? So we have definite integral, all the same width. Then we can write that f of b minus f of a is f of x sub n minus f of x naught. So let me draw the picture again so you remember sort of what we're doing. There's a, there's b, and we're dividing this region into a bunch of boxes. Let's do rights just for fun. Okay. There, and then, okay, that one's a little short. Remember that this one becomes x sub 0. This is x1, x2, x3, and this one's x4 because I chose 4 boxes. Or you can call them a sub 1 and so forth, all right? In here they're using x sub n and x sub 0. B is the last one. X sub 0 is the first one, that's a, so they just substituted. Now, what they did next, do you see what they've done in here? They've played a trick we have used before, but not terribly often. What did they add right there?
0.
They added 0. Remember that some of the things that you are always allowed to do include multiply by 1, anytime, anywhere, as often or as little as you like, or, what's the second one? Add 0. You can divide by 1, but add 0 is the second major one, all right? We don't use it as often as multiply by 1, but we do use it occasionally, and they're using it here. They're adding in these intermediate steps here. And by adding them in, they're able to create this summation between 1 and n of f of x sub I minus f of x sub I minus 1, the one in front of it, all right? So basically they're taking that height and subtracting the height in front of it from it. All right, so they're taking the right endpoint minus the left endpoint height. Okay, that's what they're doing. All right, now we know that f is some antiderivative of the integrand, lowercase f, so that gives us the mean value theorem. The mean value theorem requires 2 things. What's required for the mean value theorem? Continuous on the closed, which I said is really an overstatement. You can have a finite number of discontinuities, and differentiable on the open. Now, how did we get differentiable? Because f is an antiderivative. If f is an antiderivative, it undoes the derivative, then I must be able to take the derivative of f. So that tells me that f is both continuous and differentiable. So I've got the mean value theorem, and because I have the mean value theorem, it means there has to be some point in every interval. In each one of these, I should be able to find a C1 and a C2 and a C3 and a C4 where what is true? The slope of the tangent line equals the slope of the secant line. That's correct. So if I have a point where the slope of the tangent line equals the slope of the secant line, then I should be able to write this down here, right? This, of course, is the difference in the two x values. Normally it would be underneath this part. So normally we would have f of x of I minus f of x of I minus 1 over x of I minus x of I minus 1. This is the change in the y values. This is the change in the x values. This is the slope of the secant line, right? This is slope of secant line. And f prime of c is the slope of the tangent line, right? That's what we have. So this has to equal some f prime at c sub I. Somewhere in that box is a point where the slope of the tangent line there is equal to the slope of the secant line. And let me draw them for you. There's the secant line. So somewhere in there, there's got to be a point where the derivative slope is the same, right? Now what they did next was they moved the x of I, the difference in the x values, over here next to the f prime of c sub I, and they substituted this up into the previous equation, which basically says that f of b minus f of a, which is what they had here, which was equal to this, this now has to be equal to f of c sub I times delta x. The delta x is coming from the difference in the two x values, right? That's the delta x. Why did they switch from f, capital F prime of c to lowercase f of c? What is a prime of x equal to? It's just the function. And here they're using capital F as an antiderivative, which means that the derivative of the antiderivative, okay, I just said it. The derivative of the antiderivative, I'm a dog chasing my tail. What did I do? I took the derivative and I antied it, which means I did nothing, right? The derivative of the antiderivative does nothing, gives you back the original function f, lowercase f. So they're able to replace this with lowercase f of c sub I. Then they take the limit of both sides as n goes to infinity. Why does this side not have a limit on it? Why does f of b minus f of a not have the limit still written there? It's closed. It is closed, but why? Why did they drop the limit on that side? They're constants. Capital F is an antiderivative function. If I plug in b, I'm going to get a number. If I plug in a, I'm going to get a number. What's the limit of a constant? The constant. So the limit on the left drops out. The limit on the right becomes the very limit that we defined for the definite integral. Right? So this is our proof of the fundamental theorem of calculus part 2. Right? Now, how do you use the fundamental theorem of calculus? Let's do some examples. I think the easiest way to do it is just to do a lot of them. So I want to do a bunch of those now. Calculus Part 2. All right. So we're going to run through a bunch, then we'll get into a little bit of what's in section 5.4. I'm not going to spend a lot of time on 5.4. It's a relatively short section, and in terms of importance, there's not a lot in there. 5.5 is more important, so I'm going to spend more time on 5.5. Okay, but let's run through some definite integrals. How would you do that integral right here? And yes, your book is kind of waiting to give you some of the trig and natural log and exponentials until 5.6 and 5.7. I'm not doing that. We're doing them now. All right? There's no reason to wait. Okay. The only ones we'll wait on are the inverse trig ones. And I'll be honest, I don't emphasize inverse trig in Cal 1 because the only way to do the inverse trig derivatives and integrals in Cal 1 is by literally memorizing a formula. And I'm not big on memorizing formulas. There is a technique we'll learn in Calculus 2 where you derive the formula. All right, so you will learn how to get the formula, which I think is more useful because you may forget the formula, but if you know how to apply the method, you can get it back.
I'm sorry, which formula are we talking about?
Those are the ones for the derivative of arc sine, arc cosine, all of those inverse trig ones, right? The ones where you feed it the number and it gives you back the angle. Yeah, you didn't like these, right? These were pretty awful. They were 1 over, like the arc tangent is 1 over x squared plus 1, right? They're pretty awful derivatives. Undoing them is just as nasty, all right, as you might imagine. And again, we will cover them, but I'm not big on testing on them in Cal 1 because I think they're better done in Cal 2, right? There's a better method for Cal 2. All right, so back to these, but trig is fair game, all right? Not inverse trig, but regular trig, that's totally fair game, all right? So how would you calculate this definite integral? This is not one whose graph is going to produce a geometric formula that you can use to compute it. That's what you have been doing, right? You have been getting rectangles, triangles, trapezoids, and semicircles, right? This is none of those, so that won't work. So what you're going to do is you can split it. The integral of a sum is the sum of the integrals, so you can split it into 2. Don't lose your limits of integration, and each definite integral gets its own differential. Remember that this symbol is huge. The entire curve sticks below the line, halfway into the line below, and the top part halfway into the line above it. It's like 2 lines long. It's really wide. And the actual stuff is written somewhere around the middle of it. Just not even with the bottom of it. All right, that's the way it's written. So we're going to split it. What is the antiderivative of sine? Negative cosine. So you're going to write negative cosine of x. I can choose any antiderivative I want. I could choose negative cosine of x plus pi, negative cosine of x plus 4, negative cosine of x plus 3, negative cosine of x minus 5. Which one am I going to choose? Negative cosine of x plus nothing, right? That makes it easier. And I'm going to evaluate this between negative pi over 4 and 7 pi over 4. So the long vertical bar means to evaluate it between the limits of integration, right? We're going to finish the first one and then we'll do the second one. That means literally, do you see this negative here? What could you do? You don't have to, but you could do what to get rid of the negative? I could flip the limits of integration, and I could write this as cosine of x between 7 pi over 4 and pi over 4, and that would draw the negative. Now what you do from the fundamental theorem of calculus part 2, take the upper limit and plug it into the antiderivative. So this becomes the cosine of negative pi over 4 minus the cosine of 7 pi over 4. It's always in that order. Upper limit plugged in minus lower limit plugged in. All right? This is where the negatives can be tricky, which is why this changing the sign by switching the limits of integration is useful, because you can imagine if this is a negative, then you're going to have the negative from the subtraction, and the function is negative. It gives you a double negative. It can make your life miserable. Okay? So watch the negatives. They can be really tricky. What is the cosine of negative pi over 4? If you're talking about the unit circle, where is negative pi over 4? Quadrant 4, and it's halfway, right? So it's the one where the values are the same, so it's got to be 1 over the square root of 2. Cosine is which coordinate, x or y? It's x. Is x positive or negative here? So this is 1 over the square root of 2, or if you like, square root of 2 over 2, whichever form you prefer. Yes, where is 7 pi over 4? It's the same place. Okay, well that's weird. So what did I get here? I got the same thing. So how much area is that? 0. That gave me nothing. All right. Take a look at this one. All right. Let's look at the antiderivative for cosine of x. This first one gave me nothing. All right, and I'll show you why in just a second. All right. There's a definite reason why, which segues very nicely into the next section. All right. What about cosine of x? What is an antiderivative for cosine? Sine. So this becomes plus sine of x between negative pi over 4 and 7 pi over 4. There's no reason to reverse the limits of integration because it's positive, so I wouldn't do it, right? I only do it if I think it will help clean up negatives. So then I plug in the upper limit, sine of 7 pi over 4, minus, it's always minus, the sine of negative pi over 4. Do not make the trigonometry mistake of assuming the negative inside the argument can be canceled by negative outside. It cannot. All right? The trig function is a line you cannot cross. So the sine of negative pi over 4 is the sine of this, but in quadrant 4, sine is the y coordinate, so it is negative. This is negative, but that's another negative, so I have a negative, 1 over the square root of 2. That's a double negative. I told you the negatives, they're everywhere, right? Okay, what about the sine of 7 pi over 4? It's the same place. What's that going to give me? Same value. It's going to be negative 1 over the square root of 2. What do I get? Why am I getting 0? Anthony?
On my table it says that 7 pi over 4 is the square root of 2 over 2.
It is the same.
Oh, okay.
So square root of 2 over 2 is equal to 1 over the square root of 2.
Oh, okay.
All right? Because you can think of the 2 as the square root of 2 times the square root of 2.
Okay.
Right? Because that gives you a 2. And then one of those cancels.
Oh.
Right? I prefer the 1 over square root of 2 form. But either one's fine. They're both good. Right? I'll take it. All right. Now, why 0 area? What did we talk about previously that would indicate why I might have 0 area?
Width or a length, but not a width.
No, I definitely have width. And you know what sine looks like. You know what cosine looks like. You know they've got to have height. You know they change between those. What's going on?
Oh, because they cross the axis.
It goes over the x-axis, and I have negative area, and I have exactly the same amount of area below the axis as I have above the axis. That must be what happened. let's take a look. I'm going to erase the work, but I'm going to leave up the integral. And let's take a look at the function between negative pi over 4 and 7 pi over 4. So let's put it into Desmos. Okay, so where's negative? Oh, okay, there's negative pi over 4. And 7 pi over 4 is here. Let me see if I can get it so that's just about all that's showing up. Bingo. That is the region we're talking about. So tell me what you see.
It's the same amount of positive area as negative area.
I have the same amount of positive area as I have negative area, and that is why I got 0. It doesn't mean there's no area. It means I have the same amount above the x-axis as I had below. All right? Does that make sense to everyone? So weird things like this can happen. All right? Let's look at another one. How about the integral from 0 to 1 of x minus the square root of x dx? Now, I'm going to start easing you towards where I hope you will eventually go, but you may not be ready. If you're not, that's fine. Don't do it this way. Eventually, you will get to the point that you do not need to split these into two integrals. You will do the antiderivative of each term individually, all right? So, first off, in order to do the antiderivatives of these, I would rewrite the radical of x as x to the 1/2 power. And you can either do it directly above it, or you could rewrite the whole thing, whichever one you find more makes more sense to you. Give me an antiderivative for x. Raise the power by 1, divide by the new power. That's undoing the power rule. The negative is a constant. It just pulls through. It's just there. What is the antiderivative of x to the 1/2? Raise the power by 1, 3/2. And dividing by 3/2 is the same as multiplying by 2/3, the reciprocal. Do I need a plus c? Why don't I need a plus c? Well, when I plug in the limits of integration, even if I had it, it would cancel, right? It would subtract itself out. So I don't need it. I'm choosing the antiderivative where c is 0, but I do need to plug in the limits of integration. The long vertical bar is not optional. It's part of the notation. It's got to be there. Which one do I plug in first? Always the upper, in this case the 1. So now this is sort of a personal choice, and I suppose it just depends on how you think. I have some students who do both the 1 and the 0 on the first term, and then they do both the 1 and the 0 on the second term, then they combine everything together. That confuses me. I don't do it that way. I plug in the 1 to everything, then I put a big minus, big parentheses, and then I plug in the 0 to everything. That works out better for me. You can do it either way. They're both correct, they both work. So what I mean by that is you could write x squared over 2 between 0 and 1 minus 2/3 x to the 3/2 between 0 and 1, and do them separately. That's fine. Or you can do them together, all right? Here's what it looks like together. First I plug in the 1, 1 to the 3/2. 1 is always a great number to plug in, so is 0, because 1 to any power is 1. Yeah, we love 1. Okay, 1's awesome. So is 0, because 0 to any power is 0 unless the power is negative, and then it doesn't exist. Okay, so I plugged in the 1. Now to plug in the lower limit, I have to subtract it. The subtraction is part of the fundamental theorem of calculus part 2. Everything after that goes inside the subtraction. So open up big parentheses or big brackets or something. Now plug in the 0. Well, what is 0 squared divided by 2? 0 minus, what is 0 to the 3/2? 0 times 2/3, 0. I told you we love 0. 0 and 1 are our favorite numbers to plug in, because what does that give you? Nothing, right? 0. So this basically ends up being 1/2 minus 2/3, get a common denominator of 6. 3/6 minus 4/6 is a negative 1/6. I think I did that right. You have area both above the axis and below the axis. Where do you have more area? Below. If this were a velocity function, this tells you that your displacement ended up negative 1/6. You ended up south of where you started, because you are displaced in the negative direction. You ended up south. Does that make sense? All right. Would you have gotten the same thing if you did it up here? Yes. You'd have 1 squared over 2 minus 0 squared over 2 minus, and then you'd have 2/3, 1 to the 3/2 minus for the fundamental theorem of calculus, minus for the function, 2/3, 0 to the 3/2. But again, you have a double negative there, right? You would end up with the same negative 1/6. Okay? Make sense? So the fundamental theorem of calculus part 2 puts together the antiderivative function with calculating the area under the curve. Right? Puts the two together. Let's mix it up and do a natural log and e to the x. Again, I am not waiting. So you are welcome to start the homework in 5.6 or 5.7 whenever you want. I would hold off on the inverse trig functions, the arc functions, but other than that, you're free. Okay. Though I'm sure you're not really wanting more homework, right? You're like, no, I'm good. I'll wait. Okay. Give me an antiderivative to e to the x. It's e to the x. We love e to the x. It's our all-time favorite function to integrate. Evaluated between 0 and the natural log of 8. So I plug in e to the natural log of 8 minus e to the 0. Remember that the e and the natural log have to touch. There can't be anything in front of the natural log. If there is, you've got to push it back inside before they can undo each other. But they are one-to-one inverse functions, so what does that give you? 8. What's e to the 0? 1. What do you get? How much area, this is a wild idea, how much area is under the curve of e to the x between 0 and the natural log of 8? 7 square units. If they were feet, you need 7 square feet of paint to cover it, right, for carpet. Okay? Let's do another one. Let's suppose you had this. Now, if you're looking at this one, unfortunately, we do not have an undo product for integrals. We have a product rule for derivatives, and we will spend a huge amount of time in Cal 2 trying to figure out how to undo that, all right? But not in Cal 1, which means you can't deal with the product. So what are you going to have to do? You got to multiply it out and get rid of the product. So this part right here would give me x squared minus 2x minus 4x minus 6x plus 8. So I could rewrite it as the integral from 0 to 4 of x cubed minus 6x squared plus 8x with the differential dx. Then individually split it up in your head, or yes, you can rewrite the integral 3 times, but that gets tiring, right? What's the antiderivative of x cubed? X to the 4th over 4. What's the antiderivative of negative 6x squared? Negative 6x to the 3rd over 3, and the 6 over 3 will reduce to 2, plus 8x squared over 2, and the 8 over 2 will reduce to 4. And then you're going to plug in the limits of integration from 0 to 4. Okay? So I would go ahead and reduce those, at least write it down so you can plug them in. I prefer to plug in the 4s all the way across, put minus, put big parentheses, then put in 0 for all of them. The reason I prefer doing it that way is you are less likely to mess up negatives, all right? And I'm all about not messing up the negatives, okay? So plugging in the 4, I get 4 to the 4th divided by 4, minus 2 times 4 cubed, plus 4 times 4 squared, minus, okay, now think for a minute here, every one of the terms in your values here in the integral, what you got out of it, the antiderivative, every one of them has an x. What's going to happen when you plug in 0? They all go away. So don't even bother, right? There's no point. 4 to the 4th over 4 is 4 cubed, which is 64. 4 cubed is 64. Double it is 128. 4 squared times 4 is another 4. Yay. What happened? Interpret.
The 64s cancel.
They cancel, and so what do I end? Well, the 64s don't, but they double, but that will cancel the 128. So what do I get? What do we have here? I must have the same amount of area above as I have below. So let's take a look at it. And I'll put this one in. It was x minus 2, x minus 4. Between 0 and 4. There it is, with all of my writing on top of it. We're talking about from here to here. Do you see this bubble up? This bubble down? How much area is under here? How much area is under here? 128 square units. I have 128 above and 128 below. And they cancel and give me 0 net area. But I would have 256 total area. So if this were describing a velocity function, because my result was 0, where did I end up after my trip? Right back where I started. All right? When it's a velocity function, the value of the definite integral is the displacement. That net value is the displacement. On the other hand, how far have you traveled? 256 miles. You went 128 miles north, and then you came 128 miles south, and you ended right back where you started. All right? And this, of course, is not the position graph. This is the velocity graph. Right? This is the graph of the derivative of position. Okay. Everybody okay with this so far?
The absolute value. struggled with that one.
There was one on the homework. Let's look at, I think it was 7. Okay. Problem number 7. Okay. So if you get a problem like this, now this is in the section where you're still supposed to be using geometry to do it, right? Which you can use geometry to do it. But now that you know the fundamental theorem of calculus, you can use the definite integral to check your answer and make sure it's right. Okay. So if I'm looking at this function, my function is 5 minus the absolute value of x minus 13.5. All right, that's the function that I'm trying to graph. All right. So first thing I need to do is define what the absolute value is. And you are supposed to know this, but I generally find that students don't, right? I mean, I get it. You do know it and you don't know it. You know it, but you don't know how to use it, is typically what happens. What's the definition of the absolute value of x? It's x if x is greater than or equal to 0, and it is negative x if x is less than 0. Do realize that negative x is a positive value, right? Because I would only use this if the x itself were negative, so that's negative times a negative is a double negative, which makes it positive again, hence the absolute value. So what is the absolute value of x minus 13.5? Let's do the definition again. What's it going to be? I want you to do exactly what we did on the first part, but do it for the second part. This is going to stay the same and be x minus 13.5 if x minus 13.5 is greater than or equal to 0. When would x minus 13.5 be greater than or equal to 0? When x is greater than or equal to 13.5. But you find the definition by setting it up just like that one. So this is when x is greater than or equal to 13.5, which you know instinctively. If it's 13.5, I get 0. If it's bigger than that, I get a positive number anyway. If it is not greater than or equal to 13.5, what am I going to have to do to this? What did I do up here? I negated the whole thing. How do you negate a binomial? You put it in parentheses. And this would be if x minus 13.5 is less than 0, meaning x is less than 13.5. This would be negative x plus 13.5, right? Is everybody with me so far? Okay, next step. Now that we know what it looks like, I have two lines. I have x minus 13.5 and negative x plus 13.5. What does x minus 13.5 look like? This is kind of a nasty graph. The 13.5 is just obnoxious. Okay. I declare this to be negative 13.5. All right? There it is. Okay, so it crosses the axis here, and then it goes up with a slope of 1. But I'm only supposed to be graphing this from 13.5 out, right? So somewhere over here, I declare it to be there, I have 13.5. So from here up, I have that graph. All right? Where would you get this graph? This would be negative x plus 13.5, and I declare 13.5 to be there. So it would be coming down like, there it is, right? Now what? What does the negative do to it? Turn it upside down. Now what does the 5 do to it? Shove the whole thing up 5. I declare u to be 5. Okay. There it is. Now you have to compute it. All right? Does that make sense? Okay. So then you will want to, and we're supposed to be integrating from 10 to 17. So if I were going to integrate from 10 to 17, you could use the different ones. One thing that might make this one a little bit easier to calculate, we can use some of our rules. Where do I have to switch the lines? What value? What number? 13.5. So where should I cut this integral? I'm going to cut it at 13.5. So I'm going to do the integral from 10 to 13.5. And then I'm going to add to that the integral from 13.5 to 17. If I'm between 10 and 13.5, which of these two should I be using? Upper or lower? The lower one. So if I'm using the lower one, that's negative x plus 13.5. Can I substitute that for this absolute value? Yes. So I have 5 minus parentheses negative x plus 13.5 dx. Right? What about up here? Which one should I use? The upper one, x minus 13.5. Make sure you put it in parentheses. Dx. And that would be a simpler way of doing it. Okay? So if you would, I've given you like 4 different ways. Pick one. Pick your favorite and do that. I would probably use this last one. And what I would do is I would simplify the 2. So this would give me the integral from 10 to 13.5 of, well, this would be a double negative. So I'd have 5 plus x minus 13.5. So that would give me x minus 8.5 dx, right? And then over here, I would have 5 minus x plus 13.5. So this one would be the integral from 13.5 to 17 of negative x plus 18.5. Right? And dx, don't forget the differential. So basically what you're doing is this half is this part, and this part is this part. And I would draw those 2 lines and integrate them over that area. That's what I would do. Geometrically, right? That's what I would do geometrically. If you were doing the fundamental theorem of calculus, it'd be simple, right? You just have x squared over 2 minus 8.5x, plug in upper, plug in lower, you're done. Okay, does that make sense? Questions? No? You guys look very tired. Okay, let's talk for a few minutes about odd and even symmetry, and then I want to do a U substitution. I can get into that. All right. So let's look at, so we're actually now into that next section of 5.4. There's not a whole lot in 5.4. A lot of it has to do with the velocity, the displacement, and the total distance traveled that we've already talked about. So I don't want to talk about that stuff, but I do want to talk about even and odd functions. So if you have an even function, what's our most common even function that we talk about? It's x squared. So if we talk about x squared, what makes it even is that if you plug in negative x in place of x, it doesn't change the function, right? Replacing x with negative x doesn't replace it. In other words, even functions are y-axis symmetric, right? So these are all y-axis symmetric, right? An odd function, what's our most famous odd function? X cubed. That's why they got the names even and odd, right? Even was named for x squared because 2 is even, and odds were named for x cubed because 3 is odd. All of the power functions, x squared, x fourth, x to the 6th, x to the 8th, they're all even functions. All the odd power functions are odd functions. But there are other functions like that as well, sine and cosine. Which one is even, sine or cosine? Which one's symmetric with respect to the y-axis? Here's one of them. And yes, you need to know, that's the other one. Cosine. Cosine is the even one. Cosine is even because it is y-axis symmetric. So cosine of x equals cosine of negative x. And sine is odd. And that means the sine of negative x is negative sine of x. So that's what makes them odd. So our most famous odd, of course, is the cubic. And when you put in a negative, it doesn't give you the original, it gives you the opposite of the original, negates it, right? Now this can have a big effect on doing definite integrals. So tell me what you think might happen if I told you to integrate sine between negative pi over 2 and pi over 2. First, you have to visualize what sine looks like, and then visualize what from negative pi over 2 to pi over 2 looks like. You know you're going backwards some, right? Because you have the negative. Pi over 2 is here, and negative pi over 2. Tell me about these areas here. They're equal. What do you expect to get out of that? 0. This is called exploiting symmetry. Could you calculate it? Yes, of course you could. What are you going to get? 0. But you could also just look at it and go, that is a y-axis symmetric function, and my limits of integration are equally spaced on opposite sides of the y-axis. I'm going to get nothing, or not an even, an odd function. So I have just as much area below as I have above. So they're going to cancel, I'll get 0, right? What would happen if I did cosine over the same region? Let's put the cosine picture up. Right. This is negative pi over 2, and this is pi over 2. Tell me about that area there and that area there. Given that cosine is an even function, which means that it is y-axis symmetric, these two halves lay exactly on top of each other. Because they lay exactly on top of each other, how much area do you have to the left of the y-axis compared to the area to the right? It's the same. Now how can I exploit that? Remember how I talked about negatives being a pain? Yeah, that has a negative on it. So I could instead double the area and go from 0 to pi over 2. just go from here to here, but double it, because I would be computing that area, but that area has to be the same. Would it work if you worked it out here using the antiderivative function? Yes, you'll get the same answer, but you can also do it this way. What's an antiderivative to cosine? Careful. Other way around. You're undoing the derivative. Whose derivative is cosine? Sine, not negative sine. So this is going to give you 2 sine of x between 0 and pi over 2. I can almost do this in my head. What is the sine of pi over 2? 1 times 2. What is the sine of 0? So it's 2. So how much area was here? 1. And how much area was here? 1. All right? So you can exploit symmetry to save yourself a little bit of time. All right? There are some rules about even and odd functions. If you know them, it helps. If you don't know them, it won't kill you. You can still get an A, but you may end up doing a lot more work. Let's say I did the product, the quotient, provided it's defined, the sum, the difference of even is even. What did I just say? If I asked you to do x squared plus cosine of x, is that an even function? X squared plus cosine? Yes, it is, because they're both even, so their sum is even. How about x squared cosine of x? Yep, their product is even. Cosine of x divided by x squared? Yes, provided I don't let x be 0, their quotient is even. So anything you do to combine 2 even functions produces an even. Odds are different and more difficult. What about raising them to powers? Powers are a little bit harder. Odd to odd is odd. All right? Odd to an odd is odd. What do you think even to an even power would be? Like if I took cosine of x to the x squared power. Should be even. All right. What about, I've lost track. Even to odd. This is the weird part. Even to odd is still even. What about, what have I not done? Oh, odd to even. What about odd to even? It's still even. It is really hard to get an odd function. There's only one way with powers to get an odd, and that's they're both odd. Odd to odd is still odd. But otherwise, if you mix in an even, it just dominates, and you're stuck. Now, we didn't get into U substitution, so probably what I will do is I'll prepare a video lecture sometime over the next couple of days, and I'll post it for you to watch at home before you come back on Monday. All right? So you have 5-1, 5-2, 5-3 due this weekend. You should be working on Python 2. Watch the video on U substitution, and then we'll come back on Monday and wrap up U substitution. Okay? We'll have to turn everything in on paper.